Welcome, chemists! Today we are going to be talking about how to read a potential energy diagram of a reaction. Our learning goals for this video are to use a potential energy diagram to identify the potential energy of the reactants of a chemical reaction, the potential energy of the products, the heat of reaction, the activation energy of the reaction, and the activated complex in the reaction, all using a potential energy diagram. Let's start by taking a look at the bones of the potential energy diagram, the axes of the graph itself. On the y-axis, we have potential energy, often measured in kilojoules, kJ. This is a measure of the amount of stored energy within chemical substances. That energy can be released if those chemical substances undergo a chemical reaction and form new molecules that have less potential energy. In that case, energy gets released as the reaction goes forward. The x-axis shows the reaction coordinate. That's really just a fancy way of saying what is happening at the reaction at each time. So really, you can think of reaction coordinate as being similar to time while the reaction is happening, and different points on the x-axis represent different substances being formed as the chemical reaction proceeds. So let's go through an example. This is going to be an example that you're probably somewhat familiar with, that of a candle burning. Now, you may not know that when a candle burns, the chemical reaction that's occurring is actually between the wax, which as a liquid moves up through the cotton wick, and oxygen gas. So the wax and oxygen gas are chemically reacting when a candle burns in a combustion reaction. Do you remember what the products of all combustion reactions are? Think back for a moment. They're carbon dioxide and water. So when a candle burns, we see heat and light because the reaction is releasing energy. And as the wax reacts with oxygen gas in the air, carbon dioxide gas and water vapor are being produced. Let's think about how we would map out this reaction that I just started on a potential energy diagram. Let's set ourselves some amount of potential energy that all of the reactants together had, the sum of all the potential energy of the reactants. So again, my reactants here would be wax and oxygen gas in the air. Let's say that I have where that red line is. If I match that up to the y-axis, that is the amount of potential energy. Notice that I'm not putting numbers on my y-axis right now. I'm just saying this is an amount of potential energy that the wax and the oxygen had before I lit the candle, right? So I'm going to blow the candle out so that we can start from the beginning here. We've got the reactants. They're sitting. They're not reacting. Now, I know I'm going to ultimately end up with a product that is carbon dioxide and water vapor. So that's going to be the product of my reaction. I'm going to take the substances, the atoms that are in wax and the atoms that are in oxygen gas. So carbon and hydrogen and wax, oxygen and oxygen gas. I'm going to rearrange those atoms, break bonds and form bonds, and I'm going to end up with water and carbon dioxide. Candles burning really has so much going on. Now, to do that, I'm going to be releasing energy. Not all chemical reactions release energy, but this is an example of one that does. So the potential energy of my products is going to be lower than the potential energy of my reactants, because to get from reactants to products, energy gets released in the form of heat and light. Therefore, the products have less energy than the reactants had, if we're talking about potential energy, because we've seen energy leave the system. We've seen heat and light leave as the combustion reaction is occurring. Before I do anything else to my potential energy diagram, I just want you to notice, if I wanted to know how much energy was in the reactants, so if I wanted to come up using this graph, if I wanted to come up with a number that told me how much energy was in the reactants, I could look at where the reactants are plotted on the y-axis. So interval A, if we look at my potential energy diagram, the distance from the reactants line on the y-axis down to a y equals 0, right? That's going to tell me the amount of energy that my reactants are starting with. If each unit here on the y-axis represents 1, then the reactant's energy would be 12 kilojoules. I'm not saying that that's what the reactant's energy is because I haven't labeled the y-axis, but that would be how I would read the y-axis. And so that would be the potential energy of my reactants, literally just reading the y-axis where my reactants are. I could do the same thing for my products, and then I could figure out the heat of my products or the potential energy of my products by looking at how my products line intersects with the y-axis and where it falls on the y-axis that way. So right off the bat, the very beginning of looking at this diagram, I can see that there's going to be a difference between the potential energy of my reactants and my products. That is known as the heat of reaction. The heat of reaction refers to the amount of energy that is either absorbed or released by a chemical reaction. In this case, we are releasing energy because the candle will release heat and light. Some reactions absorb energy. We are now going to think about what happens when the reaction actually occurs. How do we get from the reactants line to the products line on this diagram? So let's light this candle. Let's get this reaction going. What am I going to have to do to light the candle? Well, unless I can breathe fire, which, nope, I'm going to need to use a lighter or some matches. Notice, to light this candle, I'm going to have to add some energy to this system. Even though once I light the candle will be releasing energy. It will be lit. It will be releasing heat. It will be releasing light. I need to put energy in order to make that happen. Turns out, even reactions that you think are happening without anything require some energy to get started. All reactions have what's called an activation energy. They need to have a little bit of energy put into the system to break the chemical bonds that are involved in holding together the reactants. And so we call that energy the activation energy. And I'm going to introduce a new term for you here. The least stable substances or parts of the reaction is called the activated complex. The activated complex is, like I said, just a fancy word for the least stable intermediate. Intermediate means in between the reactants and the products. That's what the activation energy is really getting the reactants to become. It's getting the reactants to become less stable in the pathway to, in this case, becoming more stable. So my activation energy, when I go ahead and light this candle, the heat from the lighter is going to provide energy to start the reaction between the wax and the oxygen in the air around the candle. That activation energy we can think of as the source of energy to get us up that initial hill. Notice on the potential energy diagram, there's an initial hill there. Interval E represents the difference between the activated complex, the least stable point in the whole reaction coordinate, and the reactants. The lower the difference, the smaller the difference between the reactants and the activated complex, the lower the activation energy, the less energy required. The bigger the difference, the higher the activation energy. So take a moment to sketch out this reaction coordinate diagram, this potential energy diagram. Sketch it out exactly the way it is with all of these labels, with all of these intervals. And we're going to think about what each of them means in an example with some numbers next. So let's think about how we would use the y-axis to find an actual numerical value for all of this information. Let's start with the potential energy of the reactants. That's going to be simple enough. I will literally just read the axis. So 12 kilojoules because the reactants line is at 12 kilojoules on the y-axis. The products, same thing. 2 kilojoules because the products is at 2 kilojoules. If I know the potential energy of the reactants and the potential energy of the products, I can determine the heat of reaction. It doesn't actually really matter the path that I had to take to get to products. It doesn't really matter that I needed to put in activation energy and then that activation energy got released. I can literally just take the potential energy of my products and subtract it from the potential energy of my reactants to get my overall net change, my net heat of reaction. It's almost like you were trying to figure out the distance that you traveled if you accidentally took the subway stop
one way in the wrong direction, that would be like the activation energy hump, before getting off, transferring to the train in the correct direction, and actually going to your stop. Really, the distance that you traveled is just the amount of stops between where you first got on the train and where you got off the train, even though you went the wrong direction for one stop. That's why we only look at the difference between the products and the reactants when we calculate the heat of reaction. So if I take 12, in this case 2 minus 12, right, products minus reactants, I get negative 10 kilojoules as my heat of reaction. And it makes sense that it would be negative because my reactants line is above my products line on the y-axis. I have to go down negative on the y-axis to get to the products in terms of energy. Let's take a look at our activation energy now. So if we don't include activation energy in the heat of reaction, how do we figure out how much energy is required to start a reaction? Really what's important for that is the energy of the activated complex, or the tippy top of the hump of the potential energy, of the activation energy. So interval D would give me my activated complex potential energy. So that would be 20 kilojoules, looking at this axis. And I really just need to find how much did I have to travel to get from the starting point, from the reactants, up to the top of the energy hump there in that activated complex. So I'm taking the potential energy of my activated complex, 20, minus the potential energy of my reactants, 12. So my activation energy for this reaction would be 8 kilojoules. I needed to put in 8 kilojoules to get this reaction to start. Once the reaction started, it released 10 kilojoules of energy.
Let's try one quick practice problem. I would like you to take a look at how the intervals on this potential energy diagram are labeled. And I would like you to think about, for each of these reaction components, potential energy of reactants, products, activated complex, heat of reaction, activated energy, which component matches to which lettered region of the diagram. There is one less lettered region than reaction component, so you will not use one of the terms on the right. You will not have one of those matched to a letter. So pause this video and see if you can figure out which letter goes with which component. Make sure you've given yourself time to try this problem, even if you're not sure. Let's go ahead and go over the answers. So the potential energy of the reactants would be interval A. The potential energy of the products would be interval D. The heat of reaction is just the difference between A and D, just the difference between the products and the reactants, so that would be interval C. The potential energy of the activated complex is not listed as any of those letters. It would be the distance from the very, very top of the activation energy and the very, very bottom of the y-axis. So potential energy of the activated complex was not an option of a region there. The activation energy is represented by interval B. Let's check back in on our learning goals. It's a lot in this video, but hopefully you feel confident looking at a potential energy diagram and labeling the different components. In the next video, we're going to talk about what makes a reaction exothermic versus endothermic on a potential energy diagram, and we'll also use table I of your reference table to do that. And then, in addition, in a future video, we will look at how adding a catalyst changes the activation energy hump of a reaction. Nice job today.